All right, so the last area that I want to talk about is called the common ion effect. We've actually already sort of hit this before when we talked about Le Chatelier's principle. So if you need to go back to Le Chatelier's principle and review it, I would do so soon. The first thing I want you to do is write the equation or reaction associated with the Ka for the acetic acid. So pause the video now and go ahead and write that Ka equation. I'm going to continue on to the notebook page and I'm going to write that equation here. So we've got for any Ka, it's always the acid dissociating in water. Since it's a K equation, it's an equilibrium based. And then we have our acetate, which is our conjugate base of our weak acid, plus our hydronium ion. That would be the Ka equation. So previously, that's what it asked us to do. And then it wants to know what happens if we add HCl into this flask. So let's come back and look at this. So it wants to know, and for this one, it really wants to know Le Chatelier's principle. And so if we have a flask that has acetic acid, so ultimately we're starting with this weak acid, very little of it is going to dissociate. And we need to know what's going to happen if I have hydrochloric. And let's think for a moment. Let's look at this problem. It says calculate the acetate concentration if we have a solution that has both HCl and acetic acid in it. So coming here, if we have only weak acid present, so we don't have a buffer solution, so we've got just very little of it dissociating. If I put HCl into that flask, so a picture would look like this, and I've got acetic acid already in here, and then I add to it HCl. What happens to that HCl? We know it's a strong acid, so it completely disassociates in water, so we end up with H3O plus and chloride minus. And ultimately, because of that, we want to know what sorts of things do they have in common. The biggest thing you're going to notice is that is there a stress associated with this reaction? And there is a stress associated with this reaction. It's the increase or addition of hydronium ion. So this equilibrium above, this one right here, now is affected by the stress of adding HCl into it. Because remember, we don't have any acetate. We just have acetic acid, and because it's weak, very little will dissociate into acetate. So if we increase the H3O plus, if that's the stress, Le Chatelier says that there's a counteraction to that stress, and therefore it will decrease the amount of hydronium ion. And in order to do that, the reaction will shift in what direction to do that. So here we need to decrease H3O plus, so the reaction will then shift to the left in order to consume that. So reaction shifts left to consume H3O plus and reestablish equilibrium. So by doing that, what it does is it suppresses the ionization of the weak acid acetic acid. Suppresses or decreases, if you will, because even less H3O plus is generated. So this is a common ion, and we look at it, and you'll notice, I'll type it in red. Here is my common, or write it rather, in red. Here's my common ion, and here is my common ion. So because they're in common, that's why we have a stress. If they had nothing in common, we wouldn't see this, unless there was a reaction, but we don't have to deal with that. So in terms of calculation, it says calculate the acetate if the solution consists of both of these. So we're going to go back to this. We're going to come back up here and use this. So we're going to go to the next notebook page. So we're going to start with our acetic acid, our Ka equation, if you will. Excuse me.
So the problem tells us that we have acetic acid and we want to know what happens when we add the HCl. So we've got 0.015 molar acetic acid.
And we have 0.01 molar hydrochloric. Now if I have 0.01 molar hydrochloric, we know what happens with a strong acid. That means that essentially all of it goes to strong acid, or goes to H3O+. So that means up here, this is not going to be 0. I'll have 0.01 molar up here because of this strong acid. And so if I want to know, I think it asks us calculate the acetate concentration. That means I really need to know what happens after everything settles out and heads towards equilibrium. So I need an ice table in order to do that. We don't have to deal with water. We have no acetate. So that means because one of these is 0, it's going to have to shift in this direction. And then here we have minus x. And now we're going to set it up and see if our stress is what we actually expect. So we could set this up as x and 0 plus 0.1 plus x. And then here we have 0.015 minus x is equal to my Ka, which is 1.8 times 10 to the negative fifth, which we, of course, can find on a chart somewhere. And then ultimately, we can say that this is such a weak acid that very little of it, so we can assume that x is much smaller than 0.015. In fact, we can also assume that x is much less than 0.01 because very little of this acetic acid is going to generate H3O plus because it's so weak. And so then that means we can instead write this as x and 0 plus 0.1 because that x drops out, and 0.015. And then we can solve for x. And once we solve for x, we find out that that concentration is 2.7 times 10 to the negative fifth molar. And remember, x is actually equal to the concentration of my acetate at equilibrium. If we do, and if we check the assumption, you're going to find out that your assumption is valid. It is less than 5%. And another thing that I want you to note on this ultimately, so if what we said earlier was true, so for example, here we said that if we add that H3O plus, then we should counteract and it should decrease and shift to the left. So if that's the case, if we have no H plus, so if there is, for example, no H plus, I'm going to write here, if no H3O plus from your hydrochloric acid, then should the acetate concentration be greater than, equal to, or less than when there is some present? So in essence, for this problem, we'd say, is it greater than or less than or greater than or equal to 2.7 times 10 to the negative fifth? Well, if it's shifting left, that means we would make less acetate. And so what we find out is if we did this same problem and instead up here started with 0 and went through the whole work, we would find out that x is equal to 5.2 times 10 to the negative 4 molar, which is much bigger. So I'm going to bring this to another page so that we can see everything. So ultimately, I'm going to change colors here. So notice that we've got acetate concentration, and I'm going to write with HCl, and we found that to be 2.7 times 10 to the negative fifth molar. That's what we calculated. If we were to calculate using the same concentration for the acetic acid, but without the HCl present, so there would be 0 there, we find out that it's 5.2 times 10 to the negative 4 molar. So the good thing is our numbers make sense, because when we add HCl, remember it shifted the reaction towards the towards the reactants, so it should decrease the amount of acetate, and you can see between these numbers that's the case.